Hello and welcome to another video in which I take a look at the weird and wonderful world of flat earth belief. Now in this video I'm going to take a look at the horizon and consider one of the standard flat earth arguments about the horizon, which is that it's both flat and at eye level. I'm sure if you've looked into flat earth videos, you'll have seen a seemingly endless amount of these videos where someone goes out with a camera and points it at the horizon on the beach, and there's usually all kinds of some dramatic music playing, and they zoom in and out and they show that it's flat, and then they talk about how as you rise up, the horizon rises up with your eye and meets your eye, and all kinds of strange claims that they make. Well, what I want to have a look at is, particularly in this video, we're going to look at if you were standing by the seashore and you did look out to the horizon, what would you expect to see, assuming that the Earth is a sphere with a radius of 4,000 miles or 6,400 kilometres. I will stick to using metric simply because it makes the calculation simpler. Now, flat earthers often talk about eye level. They always say you look out to sea and the horizon's at eye level, and therefore that means the Earth must be flat. Well, they never actually define what they mean by eye level. It's quite a vague concept actually when you stop to think about it. So the first thing I want to do is actually give some proper definition of what we were talking about. If we're talking about someone at eye level or something at eye level. So say someone's standing on a surface like this. Okay. And there's a person there. So they're looking straight ahead. Now, because they're on a flat surface, this gives them some kind of indication of what the horizontal is. So they can look at things in the distance and have a sense that it's either above or below this horizontal or eye line or whatever you want to call it. So to give it a proper definition, if we have a line that comes from the person's eye like this, and they look along there and you see things that lie on this line, then we could say that they're at eye level. Now this line is going to be horizontal from the person's eye, so if there was a plumb line hanging down from this line, then it would be perpendicular to that line. So I think this gives us a definition of what we actually mean by eye level. So for a person standing here, it's anything that would lie along this line or be very close to this line anyway. Now what I want to do is then consider if someone's standing on a sphere with a radius of 6,400 kilometres, how close to this horizontal line will the horizon look in their field of view? Well, first of all, you have to consider what we mean by how close things are in your field of view. So if you have an eye like this, someone's eye, okay, when they see things a distance apart, the way we talk about how far apart the two things are, say you've got something here and something here, is we talk about the angle that is subtended at the eye. So we're talking about the distance between them in terms of an angle. So it's an angular distance. So this angle here would be the angular distance, if you want to call it that, between this object and this object. So it's the angle that's subtended at the eye. Now, as these two things move away, this angle will get smaller. So if they're here, they're the same distance apart in space, but you can see that the angle would get smaller. So that's why things look smaller as they move away. Okay. So that's just basically going into how we measure the distance between things in our visual field. Now, if someone's, let me draw another line up here. If someone's standing on the Earth or on a plane or something, and you want to talk about, we want to represent a person standing on the Earth, and we want to represent the distance to the horizon, okay? Now, a person would be too small to represent in here. There'd just be a little dot on there. So we can't accurately represent the diagram as showing in a sort of proportional way what we want to look at, because it's too difficult. You can't really represent it visually. Now, let's consider, say a person had a height, say I represented a person as being as a height of 1 millimetre, and I wanted to represent this line in proportion as shown the distance to the horizon, then this line would have to be about maybe 2.5 to 3 metres long. So you can see that I can't really represent on a diagram properly a person standing on the Earth and showing the distance to the horizon. So the diagrams I'm going to show you are necessarily going to be completely non-representative visually of what we're looking at, but it doesn't matter, because what matters is the mathematics, and the maths will be right. So let's go back a bit here. So we have a person standing here, okay, and their eyes are looking out like this. So this is the horizontal line, or the eye level line. Do it a bit darker so you can see it. Okay. Now, when for a person standing on the Earth, the horizon line, or standing on a sphere, the horizon line is about roughly the same distance below their feet as their eyes are above where they're standing, or the surface of the sphere. So if the person's eyes are, now we'll just take it to be simple, we'll just take it as being 2 metres, that the person's eyes are 2 metres above the surface of the sphere. Because, say if you're standing at the shoreline, and that's about the closest we get to looking at the Earth as a perfect sphere, because the water follows the curve of the Earth, then your eyes might be about 2 metres above sea level, because you might be standing just a little bit back from the shore. So 2 metres is a reasonable sort of distance to talk about. So the horizon's going to be down here, and it's going to be 4 metres below their eyes. So you've got the Earth kind of, or the sphere, curving away like this. So it kind of curves down like this. And there's a line from the person's eye. That's not very well drawn. Wait a minute. There's a line from the person's eye to this point that is the horizon. And you can imagine it kind of curves down like this. That's what it's supposed to be. Now what we want to know is, what is this angle here going to be? So we call it x degrees. Now like I said, this diagram is in no way proportionate to what we're actually looking at, because this angle is going to be way, way smaller than this. But we can calculate, using this diagram, exactly what this angle should be. Now, the distance to the horizon for a person whose eyes are 2 metres above sea level can be calculated easily. Now I'll show how to calculate this in another video that I made. You would do 6,400.002 squared minus 6,400 squared. And it gives you, that comes out as 5.1 kilometres. Okay? So the line from the person's eyes to the horizon is 5.1 kilometres. Now, we want to calculate what this angle here is. Now we can do that by using trigonometry, and it's just basically the inverse tan of, now that distance is 4 metres, which is 0.004 kilometres. So it's going to be 0.004 divided by that distance there, 5.1. Now you can use a calculator for this. Inverse tan of 0.004, 4 divided by 5.1, which gives you 0.04 degrees. So this angle here is 0.004 degrees. Now what that means is that in this person's visual field, the angular distance between the horizon and the horizontal position is just going to be 0.04 degrees. Now, in theory, that's noticeable to the human eye. The human eye can see down to a resolution of about 0.01 degrees, but I mean, that's the absolute maximum resolution you could see. If you were standing by the seashore looking out to the sea, there's no way that it would be obvious to you that there's this very small angular distance between what should be the point in the distance, which is exactly horizontal from your eyes, and the horizon. It's not going to be noticeable. The horizon line is basically going to look like it's at eye level to you, because it is only 0.04 degrees below the horizontal. So therefore, it will look like it's at eye level. Now, that's one aspect of whether we would notice that the Earth is a sphere from looking at the horizon. Would we notice that it's below eye level? Well, when you're standing at the sea, no, you wouldn't. Another aspect of it is, would you notice that the horizon is curved in the distance? Well, we can think about that as well. Now, if we're standing on a sphere with a radius of 6,400 miles, there's going to be a horizon around us which forms a circle, like this. There we go. So we've got a circle here, and this represents the horizon line. So you imagine you're sort of right in the middle of this circle, and whatever direction you look in, this is where the horizon is. Now, so if your eyes are 2 meters above the surface of the sphere, then the distance to the horizon is 5.1 kilometers. What we want to consider is how much of this horizon line do you see with your eye? Okay, how much of it do you actually see? Well, with the naked eye, the angular range that you see with your eye is actually quite small. I mean, there's a central part of your vision where you actually see things clearly, which is really quite small, and then beyond that, there's the periphery vision in which we don't see things very clearly at all. So with the eye, you're only going to see a little bit of it clearly at wherever you're looking at any one moment. But you can take photographs. Now, I looked online and I read somewhere that about the widest shot you could take before it starts to distort is about 90 degrees. So what we'll do is we'll imagine if you were standing here and you took a wide shot, angle shot of the horizon that had an angle of 90 degrees, which is, this is as wide an angle a shot as you're going to be able to take with a camera, like I said, without it starting to distort the picture. So what I'm trying to do is give it as good a chance as possible for us to possibly see the curvature of the horizon here. Now, I had to think about this quite carefully and think, how could I show that you would or you wouldn't expect to see this curve? And I thought, well, if I draw a line here, this line is going to be on a line that's on the surface of the sphere you're standing on. And if I draw another line here, what we could do is measure the angular difference between this line and this line in your visual field. If you're standing here and your eyes are about 2 meters above the surface of the sphere. Now the first thing we have to do though is work out the distance from here to here. So the distance from here to here is 5.1, distance from there to there is 5.1. Now this is a right-angled isosceles triangle, so you can just calculate easily enough using Pythagoras what the length of this line will be is. So you do 5.1 squared divided by 2 and take the square root of that. That gives you 3.6. So this is 3.6 kilometres. Okay. Now you can easily check these numbers for yourself later. Right, so let's represent this, looking at it from, rather than looking down on it, imagine looking at it from the side. Again. So you've got a person standing here. Now, the sphere sort of curves away down like this. So there's going to be a horizon line here. And this is their horizontal line. This is their eye level line. And this is the horizon here. So there's a line from their eye straight to the horizon. Now we know if their eyes are 0.002 kilometres or 2 metres above the surface of the sphere, we already know that the length of this line is 5.1 kilometres. Okay. I'll just show you, I'll just double check that on the calculator. That's 6400.002 squared minus 6400 squared. This is, yeah, 5.1. Now, like I said, you can see in another video where I show you how to work that out properly and derive that formula for you. Now, let's zoom in a wee bit here. What I want to do is calculate the angular distance between this line and another line, this line from your eye to here, which now this, wait, I'll rub that out. So this distance from here to here, this is going to be 5.1 kilometres. And this distance here is just, now we worked it out over here, it's 3.6 kilometres. Okay, so just to make it clear what I'm doing, and what I'm doing is I'm looking at, this is looking down on the situation. So the person standing here, so there's a line here, and there's a line here, and we're working out what the difference is between the angle, so the angular distance between where this line is and where this line is in their visual field. So this line is down here, and this line, the 3.6 kilometre line is here, 5.1 kilometre line is here. Now again, obviously, this is completely and utterly disproportionate. It doesn't look anything like this, but again, it doesn't matter because we can do the maths. So this angle here is going to be the inverse tan of 0.0404 over 5.1, and this angle here is going to be the inverse tan of 0.004 over 3.6. So the difference between those gives you the difference, the angular distance between this line and this line, or where this line in the visual field will be and this point in the visual field will be. And we can just do this in one calculation. So it's inverse tan 0.004 divided by 3.6 minus the inverse tan of 0.004 divided by 5.1, which gives you 0.02. Yeah, which is what I expected, 0.02 degrees. Okay, now, so let's think about what this means. This means that for the person standing here, this part of their visual field that contains the curve is all bunched up into just 0.02 degrees of their visual field. Basically, it'll just look like it's all in the same place. From here to here, there's not going to be any difference in their visual field. It'll all just look like it's on the same line. So this whole curve will just basically be sort of collapsed into a straight line in their visual field. There's no reason at all to suppose that they'll see it curve. I mean, that's assuming a 90-degree field of view, which is, it's the most extreme field of view you could get, like I said. I mean, with the naked eye, you're only going to be seeing a tiny bit of this. With the naked eye, I don't know. I haven't looked into exactly what it would be actually. I could maybe look into that for you, but, it's just going to be a tiny little range with the naked eye. So there's no way you're going to see the curvature. But even with a camera, with a wide angle shot of 90 degrees, like I said, the angular distance between this line and this line in the field of view is only 0.02 degrees. It's just not going to be noticeable. So what this means is, that for a person standing on the surface of a sphere with a radius of 6,400 kilometers, the horizon is going to look like it's at eye level. Okay, and you're not going to see the curvature because this whole part of the light, this whole part here where the curvature is that you would see, is just not going to be visible. So therefore, this whole argument that flat earthers put forward, that when you're looking out to sea and all you see is a flat horizon that's at eye level, well, it doesn't mean anything because you would see that on a sphere anyway. So therefore, it just doesn't add up as a flat earth argument at all.